Hi, and welcome back. This is problem 6. And for this problem, I'm just going to tell you how I approach story problems, because you're bound to see a story problem in one of your 2 midterms, as Professor Sahai really loves stories. We can all attest to that for all of us that took CS70 Spring 2013. And so let's get started. So you have a 3-headed dragon, and right from the outset, warrior dragon, dragon that lets warrior lives, other that eats warriors, other heads. You get this sense of noise inside the problem, but you can obviously use induction to get from point A to point B without all the noise. Now let's see what other clues we can get from this. So since it's 3-headed, we want to work with mod 3, and obviously this means that we should have 3 base cases. 3 base cases to work with. But first of all, what is our problem that we need to solve inductively? Well, if there are 2 heads that eat warriors and 1 head that keeps the warriors alive, then obviously the number of warriors are going to decrease. So at some point, the dragon is always going to win, unless you start with a large enough number of warriors. So that's where we should get started. So for all n, right, greater than or equal to 1, and obviously less than 1,000, you want to say that the warriors will run away. Because notice, no warriors come into a field. It depends on how many warriors you start with. So the number of warriors will always decrease. And so base case n equals 1, n equals 2, n equals 3, right, base cases. And obviously if there's 1 warrior, then it'll run away. If there's 2, then it'll probably get eaten by one of the 2 heads, and same for n equals 3. And then you just build on from there using strong induction. Remember, if you have multiple base cases, you need strong induction. So you assume that for all d less than or equal to n, the warriors, the n warriors that start will run away. And then you set this n to be 1,000 so that you don't even have to fight the dragon. The dragon just flees. And that is how you solve problem 6. Welcome to the final problem that I'll be recording today, problem 7. And the solutions to this problem are actually really well written, so I'm just going to go over and provide some of my own commentary. So the first thing you notice is the Fibonacci sequence is really good for induction or recursion, so that's the first thing that should come into your mind, and we're dealing with the sum. So even though we probably need strong induction, to make sure we can use our results for smaller values, we do not need multiple base cases for these, because we are not really concerned with fn minus 1 and fn minus 2. So we can see here we have 1 base case, 1 equals f1 plus f3 in fact. So the thing we want to prove holds. Now we just need strong induction, which is this condition, and a strong condition means you can do more with the inductive step. Now, one thing you want to note for any problem is you want to see what the example is, because if instructors don't want to give you too much of a hint, they might give you an example and have you figure it out yourself. So 27 equals 21 plus 5 plus 1. Notice 21 is the closest Fibonacci number to 27. And what does this leave you? This leaves you a really small quantity, and since the first few Fibonacci numbers are 0, 1, 1, 2, 3, 5, these numbers are really small, and they can give you a fine-tuned difference between whatever values you have left. So maybe you want to take the largest Fibonacci number that's closest to this target quantity here and have the other smaller Fibonacci numbers fill in the void. And this is pretty much what you see in this proof. So the example actually really helped. Now, the first case is if for k plus 1, remember, this is induction, minus the largest Fibonacci number is 0, then we only just need one Fibonacci number plus 0. Otherwise, there is this little quantity that's left over, and we can use the inductive hypothesis to say, oh yeah, this quantity can be represented by more Fibonacci numbers. However, we have two problems with the assumptions we made. So our first assumption is that we actually even have this largest number in our set of Fibonacci numbers. Because what if, like, you can get intermediate Fibonacci numbers to add together to this target value? So this is what case 1 is for. Case 1 is to tell you, let me clear this out. Case 1 tries to prove that that S is in fact included within the set of Fibonacci numbers. So in order to do this, we combine two of our proof techniques, proof by cases and proof by contradiction. Again, it's really helpful to combine the things you learn, because that is most likely how we can find advanced content to test you on. If you have if you're comfortable enough combining different pieces of material, then you know that you're ready for any exam. So anyway, that was kind of a sidetrack. So case 1, we just had to prove that S was indeed in the set, and we did that by contradiction. Usually, if you have a difficult time trying to find a proof, direct proof or proof by contraposition, contradiction is what you can rely on. But you should be careful to make sure that you don't slip up during this proof, because proof by contradiction requires a really different kind of thinking. Now, case 2 is the fact that when we assumed that this little quantity was here, the Fibonacci numbers could clash with the biggest Fibonacci number in terms of consecutiveness. And so we take a look at this here via contradiction and show that this cannot happen. And so we've covered all of the assumptions that we made, which are pretty logical based on this given example, but of course we had to prove it. And later, after proving our assumptions, we can prove the main thing. And that is how you modularly construct a proof for this problem. And that is it for video solutions. Again, if you would like, I'd like to see some feedback on these solutions. What did you like? What didn't you like? Search on Piazza, and I'll try to answer them and make them better for the next homework. See you guys later, and good luck with the course.